What's the date? 28. Dang. We're almost halfway through the semester. I think next week is halfway, yeah? 1, 2, 3, 4, 5, 6, 7, 8, 9.
So there's going to be a quiz 13.3 through 14.1 on Monday. Yay. Aw.
I actually have a handout today. Oh my God. So let's see. Last time we got into 14.1. I think we effectively finished it. Are there questions from homework stuff? Have you guys tried anything out recently? Some of you guys have been studying for other tests, I understand. If I am low on your list of priorities, oh well, what can I do about that? I understand. You have physics, you have other stuff. Math is just the most fundamental science, that's all. All other sciences require us to do anything. Yes, and we don't have a building of our own yet. What the hell? We'll get over it. So any questions from homework stuff? How are you guys doing? You alright? Is that a bad question right now? I feel like that's a bad question. Sorry. What's your favorite liquid of choice to get you through besides tea? No? Normally physicists, the further you get in physics, the more you tend towards Guinness.
Well, for me, it's a steady drip of caffeine.
Steady drip of caffeine is good. See?
IV drip.
Yes. Yes. You want to get a nurse friend to help you. You don't want to have to poke yourself. Oh, come on! Yeah, that always sucks. Or through the hand sometimes. You got nice big veins. Huh? What is that?
It's a beer.
Oh, okay. Sure, that'll help. Then sometimes things make more sense because they were actually drinking a lot of that when they wrote it. So you never know. All right, stay away from the really, really hard stuff until later. Grad school is where you pull out the all right. So no, if there's no questions from any homework stuff. So just to remind you guys, since it's coming up, 13.3 is the arc length thingamajig. I probably just put the formula on there, but it should be one of the easiest formulas to remember. That also had the normal, binormal, and the unit tangent we knew before. Right, so those formulas I'll just put down there. I'm not going to make you remember that meandering labyrinth of things. It's like I said, it's a use of these tools that we learn, right? Okay. 13.4 was just motion, so it's the same as 13.3, just calling everything acceleration and velocity and stuff like that. To be honest, it's really exactly the same. 14.1 seems like it's going to be horrendously difficult when you look at all the images and so forth, but once you get into the homework, you should realize it's really not as horrible as it seems like it might be. It's just, I mean, I want to make sure you understand the transition we're kind of making right now from chapter 12 and 13 to chapter 14. 12 and 13 are explicitly vectors, right? It's basically almost all of it is just pure vector stuff, vector functions, analyze vectors. When we made an equation of a plane, we sort of left vectors. A vector defines a plane, but then I have a nice multivariable expression that defines a plane. Are you guys kind of with me? I'm going to assume that's a yes. So now we're going back into just straight up functions of multivariables, so functions of x and y. It's sort of the same thing we were doing before. F of x, y takes the place of z. Ooh, like I said before, right? So the natural progression of things is we talk about functions, and then now we're going to talk about limits and continuity, because the next thing we're going to talk about after that are derivatives. And we're going to start with partial derivatives, because they're involved in creating these other more general types of derivatives. All right, so that's sort of where we were and where we're headed. Today we're going to focus on limits. And limits get A little freaky. You're going to have to use something. Who in here has ever used the squeeze theorem? I like it. Who in here has never heard of the squeeze theorem? You can be honest. You know, like, does that have to do with riding the subway? Squeeze in there, some jacket squeezes something or something? No. It has nothing to do with that. We're going to have to cover old squeeze theorem and see how it works for us now. All right. So enough overview. Let's get into the nitty-gritty. Let's do this here. Call. So in order for a limit to exist, let's go back in time to when we just had nice x and y, and that was it. For the limit as x approaches a of f of x to equal L, what must be true?
Has to be equal L from the right and left.
Beautiful, I love it. So good. It has to be the same from both directions. So the limit as x approaches a from below has to equal the limit as x approaches a from above.
And the limit has to equal f of x.
I like it. So, and also the limits, and then you can kind of capture all that. Well, it has to equal L, right? It doesn't have to equal f of a at all. In fact, it can be completely undefined at a, because the whole idea of a limit is, do I ever get to a?
No.
No. All right, so I used to, when I introduced it in calc, I used to think about the movie The Blob, where you see something weird and you get really, you're like, what is that? And you get close and you just don't touch the damn thing. And that's a mistake the old man made in the movie. He jumped on his arm, and the whole thing went crazy. You should see it. It's actually pretty good. The 80s movie is pretty good. Back when they knew how to make movies. All right. So that's old news. Now, but this is the key. This is the key. So I could say this in a very strange way. We would never have said this back then, but I have to, as I approach A from all possible directions, they must all agree. And of course, in 2 dimensions, it's like, from below, from above, it might not be there, it might be over there. Right? But they agree, so the limit exists. And of course, when you first learn this, you get all freaked out about that point and all that kind of shit. But the limit doesn't care about that. All it cares about, where does it look like it's going to? Are you guys with me? So now, the minute I add one more dimension to this, how many ways is there to approach that now? Infinite. I can come at it from this way. I can come at it. You know, I can just, any sound effects you want, but now on the surface of it, that sounds like, okay, that's impossible. Next topic. But the nice thing is, to disprove it is easy. If I wanted to disprove in 2 dimensions, it's almost too easy. All I got to show is like that. Well, that limit doesn't equal that limit. So if I think the limit doesn't exist, it's easier to disprove that it exists. Now, if I think it does exist, oh shit, that's where squeeze theorem becomes a very good friend. Right? Okay. All right. So leave that up there. So what we got now is this. We have the limit. Now, of course, what's an input? What kind of function am I talking about now? I'm not going to put f of x. I'm going to put. So what's going to go down here as? No. As xy goes to some ab. So remember, here's my xy plane. The carpet is my xy plane. So let's say this point right there, that x and that y, and I want to know what's the limit as I come in. Do all the limits agree? So as I approach the point AB, in the xy plane, what do the outputs do as I approach that point? But I have to consider somehow all possible directions. So thankfully, squeeze theorem is one way. There's also, I'm not going to go this route, so you might be thankful for that. The epsilon delta route you can go, right? But most of the ones I've assigned should be doable by the squeeze theorem. The squeeze theorem is just so nice. Since it's nice, it can't possibly always work, so that's true. And I want to say that this... Now, let me see if I can trip you guys up. What would I put over here that would make sense?
L something else.
No, L. I know, I tricked you. So an input is xy, but the output would be a single number, right? A z. So that's going to be a single number. I like it. I just wanted to be mean there. Or continue being mean, I guess. All right. So, I mean, it's nice to... So how do you read this? The limit as xy approaches a, b of f is L. Sweet. I like it. So, for example, let's do... See, how much do I want to put up here and how much do I want to just let you loose on? Let's start off with something nice. I mean, this you can just eat up. Hopefully. Yeah, don't overthink this, right? I mean, yeah, you just plug and chug. So you always plug the point in. What are you looking for that tells you you have more work to do? Be very specific. If it was something over 0, well, that's infinity. If it was 0 over something, well, that's 0. So specifically, it has to be some 0 over 0 or infinity over infinity, some indeterminate form. Sweet. Indeterminate freaking form. Shit. L'Hopital. You're like, I thought that was behind me. L'Hopital gets interesting because we haven't even fully defined how to do a full derivative on this stuff, right? So that doesn't exist yet. We haven't proven a L'Hopital's rule for this situation yet. But this is nice. When you plug it in, do I get an indeterminate form? Hell no, I get -1 over 5. All right, cool. So as I approach the 1, 2, from any direction, as I approach, say this is my origin, as I approach 1, 2, the outputs go to -1/5. They go under the floor. 1/5 of a foot or whatever you want to call it. Whatever my scale is. Do you guys get that? Whatever path I take, I don't have to worry about the paths because computationally it works out. So it has to be every path. It's got to somehow be, how do I want to say this? Since the limit exists there and it's equivalent to the function value, this is a little bit early for this, but then it must be what through that point? Continuous, because what does continuity add on top of this? Do you remember what's continuity add to this? Not only do the limits have to agree, but f of a would have to equal L. If that was in addition to this, then it would be continuous through A. It would be continuous through AB over there, yes?
If you got 0 over 0 and you could factor out...
Totally. I love it.
It would still be...
You got it.
Yeah.
So all the old stuff, remember when they're radicals, you might have to multiply by the... When they're radicals, like 1 plus rad xy on the bottom, you might have to multiply by the conjugate. Oh shit, remember that word? Conjugate. Isn't that from French, Jeff? Conjugate your verbs. Yeah, but you remember conjugate, right? Okay, let's do an example. Let me see if I can pull one out of here. Do they have one of those? That would be neat. Screw it. They probably have one in the homework, maybe. Do they? If they don't, then we don't worry about it. Oh, there's one. Yay. Let's take a look here. You want to, because what we're about to do is to get into a situation where if I can't do anything, if I plug it in, I get indeterminate form, but there's nothing that I can factor, and there's nothing that I can do a conjugate to, I need some alternate method, and the alternate method is the gross method, right? So, we always look first for the non-gross method. So here I see a radical minus 1. It's got a conjugate that exists, so I try that first. If it leads me down to something that doesn't work, then I got to back up and do the harder thing. So what is the conjugate going to be? So, I mean, first off, when you plug a 0 in, what do you get? Let's actually make sure that is something I got to worry about. So I get 0 over rad 1 minus 1, so I get 0 over 0. Shit. So that kind of sucks on its own. Yes?
Does Sophie-Tell's work in 3 dimensions?
So like I said, we haven't fully defined what a derivative is in 3 dimensions yet. So we'll eventually get to the point where we can define a L'Hopital's type thing. We're just not there yet. Alright, so what will the conjugate be that I multiply by?
Yes.
Do it again, sorry. What did you guys say?
Plus 1.
Rad, blah, plus 1. Exactly. Rad, blah, minus 1 times rad, blah, plus 1. So I multiply top and bottom by the conjugate to make it legal. I picked the conjugate because it's the difference of squares paired. You guys semi-remember this? And it's going to force my radicals to disappear, which is beautiful, because that's what's making this problem gross. So anytime I can kill the gross part, I will. Fill it with fire. So what do we get? X squared plus y squared, rad x squared plus y squared plus 1. Yeah, there it is. Plus 1, there it is. All over. Now here I get x squared plus y squared plus 1. Well, square root goes away, right? When I multiply those. Is that cool?
Yeah.
And then minus 1.
Right.
So I just get x squared plus y squared. Now let me let you guys, does everybody agree with me there? You don't have to agree with me just because I'm the teacher. I obviously make mistakes, so what the hell? This times this is that. Radicals go away. Negative 1 times 1 is minus 1. It kills that plus 1, so you're just left with x squared plus y squared. And of course, what happens?
You kill this too.
Yeah, do you remember if you took me for 180, I said you're killing the problem? 0 plus 0 is 0. That's the problem. Once I've killed the problem, now when I plug a 0, 0 in, what do I get? 2. 2. It's great. Holy shit. 2. Yay. So as I approach 0, 0, as I approach the origin from any direction, the output is going to be, let's say it's feet, so like 2. Whatever direction I come at it. Alright, so let's talk about this idea of direction. We call them paths. We're going to take certain paths to get somewhere. Yes, sir?
Geometrically, why, if these are the same problem, if you just essentially multiply by 1, why, how did the indeterminate form change? Like,
what we're doing is right here. What's the only time I'm allowed to actually do this? Let's take a step back. I like your question. This might be a question that people have. Let's take a step back to two dimensions, right? So if I had limit as x goes to 1, x squared minus 1 over x minus 1. That's a nice problem, right? So the same thing happens here, but I want to look at an easier problem, then I'll just say, okay, the exact same thing just happened. So what would I do here? When I plug a 1, I get 0 over 0, so I got to do something. Thankfully, there's a part that I can factor, so I do. And of course, I get... I like it. Now, right there, the thing I just did is that this function equals this function everywhere except at 1. This function equals this function everywhere except at 0, 0. And why do I not care that it's not everywhere? Because I don't even get to freaking 0, 0. So that's why I can use this alternate form. So what I just did, I didn't change the function. I made the function look different. But it still had the implied problem at 0, 0. The domain doesn't change just because I changed. But I'm not even going to plug 0, 0 in. Really. I'm just seeing what happens when I get really close to it. Yes?
After multiplying by the conjugate, shouldn't the denominator be x
But then, what's negative 1 times 1?
Yes.
All right, let me do that part by itself. So on the bottom, it was this, right? And then it multiplied by square root of x squared plus y squared plus 1, right? All right, so this time this is x squared plus y squared plus 1. Then the middle terms cancel, and then I get a minus 1 gone. I like it. Cool. All right. All right, is that cool? That answers the question. So
you just got rid.
This function is x plus 1 everywhere except 1.
So you lost the point.
I don't care about that point. So I can lose that point, lose it, because I don't even look at it.
It's not.
I don't get there. So I can use the form of the function that doesn't have a problem at this point because I don't even go to this point. I really want that to make sense. This is... What's up? Are you okay? Like, you look like you're in a park, man.
Are we going to have to go through this using that formula from...
No.
Okay, thank God.
No. Are you worried about like the limit definition of derivative? No, you've gone through that once. Why would I don't want to go through that. All right. Okay. Let me see. Are we ready to give this to you? I think so. Quick thing about squeeze theorem, and I'm going to give you this little handout that I want you guys to work on. Just to remind you, or to show you for the first time, maybe. I don't know. So I'm going to show it to you in 2D, and then I got an example on this little handout in 3D. Works the same kind of way. Oh! Before we do this, I forgot, I do need to talk about the paths thing. I got sidetracked, sorry. The idea of a path is really strange. Let's just do something, let's see. What you got, Jeff? Sure. Yeah. All right, so we could do this. We could figure out what the limit is, right? Well, let's talk about this idea of a path. I just want to show you an example of what this means. So this is the one we can do like we just did that one. Is that cool? But just to show you what the idea of a path means, I have to pick a way to approach 0, 0. So in 2D, I could approach 0, 0 from above or below. Right? So I can follow if my function does this kind of thing, I can approach it along here. But now in 3D, I can approach it, I can keep one of my variables constant. I can approach it along the y equals x line. I can approach it along anything that's within my domain of that function, right? So I've got my xy plane. I got some covering over it. X and y are what kind of variables? Independent. So for this function, if I make x 7, is there a certain thing I have to make y equal to? No. So I can choose x and y to be the same, which means, so if I say my path is going to be along the y equals x line, all I'm saying is I'm going to make all my inputs the same components. I'm going to pick a number, and then that's going to be what I use for x and y. That's what it means. So I restrict, I set a certain relationship on my two variables that's not required in general, but that's how I define a path. So I am following the y equals x line. I'm seeing what my function is doing, oh shit, as I move along the y equals x line in the xy plane. I really want you guys with me. So I love this idea. So this is I want to strip the carpet out and just put a giant grid down here. That'd be awesome. So this is my xy plane down here, right?
Okay.
Just so it's easy for me, this is the origin. All right? Let me move over this way a little bit. So, let me see. From my perspective, that's positive, that's negative, that's positive, that's negative. You with me? So above this carpet, there's some z, there's some f of xy. There's some... So at that point, the output's here. At that point, the output's here. So it's going, doing whatever it wants to. Are you guys with me? So it could be a dome. It could be some funky sine function. It could be whatever. Okay. So if I approach 0, 0 along the line y equals x, that means I'm going to look at my function. I'm going to walk along the y equals x line and go, what's my function doing? All right, it's doing like that shit. What the hell? Right? Because that's what it means to follow a path. You're making restrictions on your inputs so that you're coming from a very defined path approaching a certain point. Because again, there's an infinite number of ways to approach any point. I like it, depending on what the domain is. Where am I? Oh, so what's this become if I let y equal x? Well, real quick, if y goes to 0, x has to also go to 0 because that's remarkable, Jeff. Because y equals x. So by doing this, it's sort of equivalent, but not really, to looking at traces of things. Now I've effectively made myself only have to worry about one of the variables. And what's this become if I replace all my y's with x's?
X to the fourth minus 1.
X to the fourth minus 1 over x squared minus 1. Is that cool?
Yeah.
And so what's the limit of this function along this path? Well, now what can I do with this? I can factor the top right?
Yeah.
I mean, when I plug a 0 in, now actually I can just see if it's still a problem. When I plug a 0 in,
You get negative.
oh, there wasn't a problem in the first.
Yeah.
Sure. It's fine. This will still work for the pathing. So when I plug a 0 in, I get 1. So here when I plug a 0 in, I get 1, which is nice. Cool. I like it. But I just wanted to get you the idea of the path. So if I chose a different path, what other kind of path could I choose? How else could you go there?
Y equals 2x.
Y equals 2x, y equals 3x, y equals mx, right? In this case, plus b won't work. But if my point involved like 0, 3, then I'd have to make my y-intercept 3. I like it, I like it, I like it. All right, linear. So that takes care of all the linear functions. Y equals mx. What else could I do?
You can do a reflection.
Y equals x squared. Y equals x cubed. Y equals x to the fourth. Oh shit. So now you see why it's basically impossible to prove a limit exists by going along every path, because there truly is an infinite number of paths. Right? Now you could collect certain paths. You could say this represents all possible linear paths.
Is that true?
Yes, because it has to go through 0, 0, right? So I don't have a plus b. So that's every possible linear path. Is that cool? So I chose the one where the slope is 1. All right. Or I could say y equals, ax squared. Y equals ax cubed. Y equals a square root of x. Y equals sine x. Y equals natural log of x. Why? But again, I only say that to tell you, thank God we don't have to do that, because that would be impossible. You would be working on one problem for the rest of your life. I'd just come check on you throughout your life, right? Until I die. And then I'll have somebody take over and come look at you. Until we're all dead. That sounds so nice. Yes?
So you can't just say all the linear paths lead to it, because that would be pretty easy in this case, at least.
Yes. So,
You don't be able to say all, even quadratic.
I like it. But let me give you an example where a limit does not exist. I might just steal one off of my sheet here. Did I do one? Yes, sure. Okay. In fact, here, I like this. That's perfect. Because what I got on the sheet is specific, and now let's do this generally. And then I'll just give you the damn sheet, so I can just stop talking about the sheet. Yeah, I like this. This is good. So I have this example on this handout, but I did this specific paths. Let's try to just choose all linear paths, which means I'm going to let y... Yes, sir.
Is that x minus 1 or x times 1?
Oh, sorry. David's got a good question. That didn't really do anything for you, did it?
Oh, okay, that makes more sense.
All right, I like it. So is this indeterminate? Let's start there.
Yes.
Yes, totally. I like it. So again, the paths thing is to disprove that the limit exists. Because if you can find paths that you take and the limits don't agree. So it's just the same idea as if I choose the path from above and I choose the path from below. and I say the word choose kind of stupidly there, because that's the only two things you're going to do in two dimensions, right? And they don't agree, then I've just shown that the limit does not exist. So now I extend that idea. If I have one path and it says the limit is 1, and another path says, it's -1, I'm done. Right? But if you do several paths and you keep coming up with the same answer, then you might step back and go, okay, now I got to use something to prove maybe that is the limit. So I got to use squeeze theorem, or maybe even something freakier, so to prove that that is the limit. How are we doing? So I always start with the path thing to get a feel for either I'm done with the problem because path A, path B, done. It didn't agree, I'm done. Or path A, path B, oh shit, they all say 7. Maybe it is 7. Shit. Maybe?
Yeah.
Okay? So again, you can do any path you want, but let's just try y equals mx. Just because it's not what I have on the sheet there. I like it. It's more generalization of what I have on the sheet. So that becomes, now what happens here? As y goes to 0, or as x goes to 0, what does y do?
Goes to 0.
Goes to 0. I like it. Just want to make sure that you still hold that. So real quick, if that was 0, 1, then I would have to make this y equal mx plus 1 so that y does what it needs to do according to the problem. Do you guys? That's why I do that quick little check there to make sure that the path I chose actually goes to the point the problem wants me to go to. Sounds like a good idea. All right. So let's see. What happens here then if I choose this? That means that I can now look at this as from the x standpoint, because now I can replace all my y's with